So look at this one. This is an example that we are adding block to the system. So when you want to adding it's like we had the blocking in chapter 5. So there we had an example that we said we're gonna have like 4 cars, and each car has like the 4 tires, like different tires. And we had another example, which is that we say we have 10 people, each person they have like they're wearing like a pair of shoes. To compare we had like a few materials for the shoe soles, so we wanted to compare them. Here is an example when we are running a 2x3 factorial experiment. We would like to run each of the 8 trials under as homogeneous condition as possible when we have the full factorial. Suppose that in a particular experiment, batches of raw material can only be produced for 4 runs at a time. Like 2 different batches will have to be used. In that case, you can say that, okay, I'm gonna have like, you see that these blocks that I would have. So what we did is that we have like the trials, like 1, 2, 3, 4, like the same thing that we had here is the same thing. So it's like A, B, C, D, like them negative, 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 like positive. So you can have the combination. You can write down, like, for example, for this row, you can put 1 as your combination, treatment combination. For this one, you can put A. And for this one, you can write down B. This one is going to be AB, and we can go like to the end of the table. And then we have the ABC. So we have like, let's say, here is said that we have the batches of raw materials can only be produced for 4 runs at a time. So we would have 2 different batch. So we would block it like for the 2 different batches. So we have the block number 1 and block number 2. And you can see here that we have the 1 and 2. So when we consider the effect of factor C, we would say average run of the 5, 6, 7, 8, right? So we had this one here for the C, for example. 5, like the positive one minus average run of the negative one. In fact, we have neutralized the effect of possible blend differences. Half the runs are at positive if they're going to be in the block number 1, and the half that they are in the the negatives, we would say that block number 2. So the rest they're the same as we had in chapter 5, like when we are considering 2 or more number of factors for so it's the same blocking that we had before. And the only thing is that here we have like more number of factors. Instead of single factor, we have 2 or more than 2 factors. You might have this question here that how we assign the trials to the blocks. Most of the time we do this. We go to the highest level of the interactions, and then we would say, okay, so whatever we have the low level in the highest level of interaction it would be in one block, and the high level in the highest level of the interaction would be in another block. Like for example, here, look at here. So ABC is the highest level of the highest order of the interactions that we would have, like is ABC, right? It's a third interaction that we have. And then we would say that, okay, so like negative, positive, positive, and then negative, like, look at here. So whatever it was in the low, we signed it for, like, we said, okay, it's going to be in one block, and then whatever it was positive in ABC, we said that it's be in the next block. Okay, so yes, let's have a summary here. Full factorials, full resolutions. So main effects and the related sum of the squares of factors and interaction can be estimated independently of one another using full factorial design. Significance of factors and interactions in the model can be evaluated using normal variety plus or analysis of variance of ANOVA. Full factorials allow effects to be determined with maximum precision by working with the average of the factor effects. Make sure that we are going to randomize. A measure of the reproducibility is always important, so we would need to replicate. Here is the equations that we have, like as a concept map. So we have the treatment, A, B, interactions, and their error. So this is the factors with two, factors with 2 factors. And with more than 2 factors, we would go with the equations that we have on this page, on page 33. Like the only main thing is that we need to find out the effect and the sum of the squares, right? And then we have the, like we would say the sum of the square of the total is that we would add all of this. For the more than two factors, basic procedure is similar to the two factor. The only thing is that when we want to find out the sum of a square, we use the equation that we had in the, like, a few pages before. I know why it's very similar to the previous one as well. It's just that when you want to think about the, like, the sum of the square, as I said, you would use a different equation. And then regression coefficient is equal to the 1/2 of the effects, including May effects and interaction effects. Or you can use the equation that we had, like we would say you have the contrast divided by the divisor. And so contrast divided by the divisor is going to give you the effect. So from the effect, you're going to find out, then you would say 1/2 of it is going to give you the regression coefficient. Okay, so that was the last slide. Make sure that you're going to look at the cheat sheet that I made for the formula. It's like you have all of those equations in chapter, it's from chapter 3 to the end of chapter 6. So all the equations, like most of them are there. The only thing is that you need to add this one to those equations, like add this slide to those equations. Yeah, that's all.